So this is when we move on to our conclusions, where we get to actually look at our results and conclude something about them. So in psych, that statistical level of significance that we use is 0.05 or 5%. So what this means is that if the null hypothesis is true, if devil's advocate friend is right, that there's nothing there, there's no difference between the groups, that means if I did this test 100 times, 5 of them, by chance, would show an effect. So a 0.05 significance level means that there's a 5% chance that we would get our obtained result just randomly. So in inferential statistics, our goal is to get a p-value less than 0.5, because this means, what this value kind of means is that if that null hypothesis was true, we want a less than 5% chance that we'd get our result. That means that it's pretty rare. It'd be really, if you got like a 0.01 kind of result, that means that there's a 1% chance that your result would have been due to chance, which you can kind of be confident is really unlikely. So if your p-value is less than 0.05, you can be pretty confident there's an effect there. So for instance, if we come up with a null hypothesis for our question we've been talking about, maybe you'd say that an apple a day has no effect on health. An apple a day doesn't necessarily keep the doctor away. If we got a value less than 0.05, if we looked at the effect between our two groups, we measured them, and we ran some statistical inferential stats on them, which we're not going to get into in this class, but there are fancy ways of comparing the two groups. If we got a significance value less than 0.05, we'd be able to reject the null. Remember, we can never prove that it's wrong. We can just kind of use our data to say that we don't support the null hypothesis. And we can conclude, therefore, that an apple a day does keep the doctor away. Now, we kind of have to ask ourselves, what do our results mean? What, are the things that I'm actually measuring real, true? So one of the things we want to keep track of is making sure the measures that we're using are what we call reliable and valid. So reliable measures are consistent measures. So they reliably produce the same results if you were to do it multiple times. And a valid measure is an accurate measure. So something that is true, it actually is measuring the thing that you think it's supposed to measure. So this kind of depiction I think is super useful. So at this bullseye, pretend you're shooting darts at this bullseye here. The dart board on the left is an example of something that is unreliable and invalid. It's unreliable because all of your different dots are kind of spread pretty far apart. So they're not really consistent with each other. And they're not valid because they're not at the bullseye. So they're pretty far off from the real kind of true goal value. Now the middle is reliable because they're all consistent with each other. Like that person who shot those darts got them all in the same spot. They were pretty good at their shot. They just were far off from the target. So they're not valid. Whereas on the right, you have measures that are both reliable and valid. They're consistent and they're exactly where they're supposed to be. That's our goal when we're doing measurements. And there are a couple different things that you can do in your research to ensure that your results are going to be reliable. So for instance, there's reliability called test-retest, which is where if you're, for instance, giving your subjects a mathematical test and you want to see what effects caffeine has on your math abilities, I don't know. Maybe you give them that test multiple times. Maybe you give them the test a day after, a week after, et cetera, over and over again, and see that if someone scores a particular thing on the test one time, they should score this similar thing on the test the other time. That makes the test reliable. If you take the IQ test now, you should get a similar score if you take the IQ test next week. That is a reliable test. Second thing you can do is what we call inter-rater reliability. So this is especially useful in an observational or descriptive type study where you have multiple people observing a particular test. So for instance, if you're counting on, if you're at a playground and you want to see the number of social behaviors a particular child exhibits, maybe you have multiple researchers all counting, all measuring the behavior to make sure that you're not, particularly biased in the way you're measuring, or you're not doing it differently than someone else. So if all of you who are observing are getting a similar value, that makes that value more reliable. We also have inter-method, which is trying to measure one feature using multiple methods. So if I want to study your math ability, maybe I give you a test of your multiplication and a test of your spatial reasoning and a test of other things. I don't know, calculus, who knows? It's getting at that question from multiple different angles, because if I was trying to study math ability and I gave you a paper with 10 addition problems on it, and I was like, see, you're good at math, great, but also that doesn't quite capture the entire feature that you're trying to get at. So it's important to use multiple methods to confirm that the measure you're trying to study is actually getting studied. And lastly, what we call internal consistency. So this means that if you have, for instance, a survey with multiple items on it, items that are related to each other on the same test should have similar results. So if you take things like the Myers-Briggs kind of personality survey, or surveys asking for your emotional health or your mental health at a particular time, if you have multiple questions that are asking you about your anxiety level, those results for those 2 points should be similar to each other. If someone says high anxiety for one answer and doesn't show similarly high anxiety for another answer, that means that your test isn't super reliable. It's getting different values. Ways to ensure validity. One is just to check your results. So to double check your stats, make sure that the results that you got check to what you predicted should happen, that kind of thing. Does the measure that you're doing actually evaluate the concept that it was supposed to? Okay, technical difficulties, hold on. Okay, does it actually measure the concept that it was designed to measure? So if you're trying to measure health and an apple a day keeps the doctor away, are you actually getting at their health? And then also, does the measure correlate with other measures of the same feature? So for instance, if I was trying to measure your health and I gave you a BMI, measured your weight, measured your physiological heart rate, things like that, those should all kind of lead to the same answer. So we want to make sure that the different measures that we use confer on the same results. Okay, so you did your study. You're like, I walked through my phenomenon, my theory, I made a prediction, I did my study, collected my data, looked at my results, drew my conclusions. Now what? Now what do I do? There's multiple things. First, do it again. Science is a process. Science is a cycle. So one thing that's important is to repeat the thing you did with a new sample to see if you get the same results. So oftentimes you might see researchers who will study a particular thing and then do an experiment 2 where they bring in a new set of people and confirm that that effect is actually a thing that they will repeatedly get. If you aren't able to replicate the thing that you got initially, that might mean the effect was just by chance or not actually there or due to a confound, that kind of thing. Second thing you do is do a meta-analysis. So meta is like extra big, like above, that kind of thing. So an extra analysis of, for instance, all previous experiments on a given topic. So maybe if I'm really curious about an apple a day keeps the doctor away, I could do a meta-analysis, a large analysis of analyses of any type of study that gave someone a healthy food and measured a health outcome, that kind of thing. And just kind of see in general, what kind of results were different studies getting? Was everyone getting consistent results? That kind of thing. Now there's a thing going on called the publication crisis. Maybe this is something you've heard of, where published studies might not actually be fully representative of all the work done on a particular phenomenon. And one of the reasons that is because of what we call the file drawer problem. So sadly, more often than not, the stories that get published are the things that find something. So if you did our study on an apple a day keeps the doctor away and found that it wasn't actually true, if your groups weren't actually different and there wasn't an effect, more often than not, it either you wouldn't feel motivated to get it published somewhere, and you would do what we just call, put it in the file drawer and move on to a different study, kind of kick it under the rug and forget it happened. Or you send it for publication and it gets rejected because it's not actually interesting. People don't actually care that you didn't find an effect. There are probably so many null effects that people got in studies that just aren't reported because people don't find it interesting or worthy of printing. So more often than not, the things that actually get printed in journals and disseminated in media are the things that found something, which is just a whole problem in itself. It incentivizes people to try to find something and make something up that's there, even if it's not really there. So we're not perfect in the field. There's a publication crisis. But, that's why, replicating and trying to recreate studies that you've done is helpful to see what's actually real.